Welcome to Mineral Talks Live, the monthly live mineral webinar that brings you in-depth and in-person interviews with mineral people from around the world. Mineral Talks Live is brought to you by a joint effort among the Mineralogical and Geological Museum at Harvard University, the SMMP, and BlueCap Productions. Tune in on the first Wednesday of every month and stay connected to your mineral world. Now, broadcasting live from beautiful Honolulu, Hawaii, the land of aloha, ukuleles, and shakas, this is Mineral Talks Live. Hello, and welcome to our May edition of Mineral Talks Live, the #1 mineral talk show on the internet. Really glad to see you there. So Mineral Talks Live is a joint operation run by BlueCap Productions, the Mineralogical and Geological Museum at Harvard University, and the SMMP. Oh my God, I keep messing that up. So we come to you the first Wednesday of every month, and what we do is we bring you personal and in-depth interviews with some of the big luminaries of the mineral collecting world. That's curators, curatorics, miners, collectors, researchers, dealers, media people, artists, everybody that we can that are somehow involved in the mineral world. And we want you guys, our viewing audience, to get to know all of the people here in the mineral world a lot better. This is an interactive talk show. So that means that you get to interact with our guests through the chat and the Q&A features, both of which are at the bottom of your screen. If you have a question about anything that our guests and I are discussing at the time, you can go ahead and fire it off in the chat area. Raquel and Eloise are usually manning that chat area. Raquel's not with us today, so Eloise is going to be managing that, and she's going to be responding to as many chats as she can, answering questions. But if there are some questions that are not being addressed that we need an answer from our guest, then Eloise will chime in during the interview, and we should be able to get an immediate answer. If your question is a little bit broader, then go ahead and type it in the Q&A section, and we'll get to those questions at the very end of the show. If you have missed any of our past episodes, there's a link right here at the bottom of the screen where you can go and you can watch all the past episodes. We've just made a major change here at Mineral Talks Live that we're really proud of and that I want to share with you. Up till now, all the episodes of Mineral Talks Live had been hosted on the BlueCap Productions YouTube channel, but now and moving forward, we have created a brand new channel for Mineral Talks Live itself. The reason being that Mineral Talks Live has become so popular that we are actually now being quoted as a source of information for different articles and people in the mineral world. So we needed to move it on to a different unassociated YouTube channel from BlueCap Productions, which is obviously a for-profit company, and just have it so that it is completely nonprofit, no money generated off it at all. The benefit for you is that for these episodes moving forward, as you check out the archives, there are going to be no commercials. So that's going to be fabulous for you. And I think you're going to be really excited by that. Other than that, nothing's going to change. All the old links work. So enjoy the shows. And we're going to get on to today's show right now. So we're going to go through the interview. And at the end, we're going to have a thing called the Quickfire 5 questions. So we want you to stay tuned for that, because for the Quickfire 5, we're going to ask our guest, who doesn't know any of these questions that we're going to ask. We're going to ask a series of questions that you as the viewers are going to see and be able to vote on prior. You're going to try to predict what our guest says, and then we're going to see how well you do at the very end of the show. So for right now, I want to say we're headed out to California, but I'm actually in California right now. So different background. We're going to head up to Northern California, and we're going to meet with Glenn Waychunas, who is an incredible scientist. We're going to talk about fluorescent minerals, which is really an exciting topic. And so with that, I want to invite and welcome Glenn to the show. Glenn, thank you for joining us today. How are you doing, buddy?
Good. Hi. Thank you. Nice to see you again.
Well, Glenn, we're thrilled that you can be here with us. Fluorescent minerals is such a fascinating topic. But before we get on to talking about fluorescent minerals, why don't you tell the audience a little bit about the work that you've done and are doing up there at the Berkeley National Laboratories and at Caltech?
Okay, well, thank you. Appreciate it. Well, I'm retired from Berkeley, although I still have an affiliation with them. So I sometimes go up there, use the libraries, but I don't do too much research anymore. But in the past, I did a fair amount of work with mineral surfaces, particularly the structure of surfaces, the structure of sorbates on the surface, and also the structure of water on those surfaces. And doing that got me involved in a lot of spectroscopy, particularly nonlinear optical spectroscopy, infrared spectroscopy, synchrotron X-ray spectroscopy, all these different tools to give you information on the molecular structure at the surface and near the surface. So we did a lot of that. And while I was doing spectroscopy all these years, I wanted to get a grant to study fluorescent minerals, and I never was able to actually get any money to study fluorescent minerals. There wasn't any particularly good torque you could use on the funding agencies to get some money out of them. So anyway, in retirement now, I'm affiliated with Caltech. George Rossman has helped me get that affiliation, and I'm working down there almost exclusively on luminescence and minerals and finding out what the activators are, looking at phenomena that are unusual and trying to unravel it. And that's been a lot of fun using his lab and also the labs in chemical physics at Beckman. And we also collaborate with Mike Gaft, who is one of the world leaders in mineral luminescence out of Israel.
Fantastic. Now, Glenn, what I usually start the program with is questions about the origin. I want to do it a little bit differently this time, but let's go back to generally the first question. How did you first get involved in minerals and fluorescent minerals specifically? At what age? And do you remember the story behind that?
Oh yeah, I remember the story very well. When I was a kid, I was very much into science, and my father bought me a big chemistry set. And in those days, chemistry sets had dangerous chemicals. I mean, you could blow up things with them, and you could poison people with them. And now you can't hardly do anything with them because everything is restricted. But anyway, I got those chemicals and started doing things with fireworks and explosives and also other sorts of interesting things, and making polymers and setting things on fire. Anyway, that led to some dangerous activity at home, and my father wanted to stop that before it got out of hand. I used to buy chemicals at a shop about 5 miles away, and this shop had scientific equipment for sale and had chemicals for sale. It also had a large showcase with minerals in it, and I was always fascinated by the minerals and liked them, and I actually bought a few, and that's kind of where things got started. And when my father brought down the hammer and said, "That's it with the chemicals. Okay, do something else," we decided to go a different way. And the shop owner there showed us in the basement how he had minerals from ultraviolet products and all sorts of
Okay.
fluorescent minerals. We had seen that before, and it was fascinating. So my father bought me a small UV light with some rocks, and that's how it got started. And I was probably about 12.
Wow. Okay. So then where did it go from there? You're 12 years old. You're now been introduced to the world of fluorescent minerals.
Mm-hmm.
And what happened then?
Well, one of the things that happened is that my father got very interested in the minerals too, and we went to Franklin, New Jersey. Of course, that was one of the first
Mm,
places we went and did some collecting. I had that little light that you could barely use, and you had to plug it in, and so there was a little house there you could go in at the buckwheat dump, and you could plug it in, and you could look at the rocks. It's a very hard way to collect that way, particularly because we didn't know what to look for by eye with the
right.
flashlight. But later on, we got a better light, did some better collecting, and got some interesting material. And this is a long time ago, so actually at the buckwheat dump, you could collect some nice things. So that started off, and then we started going other places for fluorescent minerals and aesthetic minerals. Balmat, New York, where there's a lot of talc minerals. The people who are tuning in probably know about Balmat and other places around the country, down in the northern Ohio, where there's a lot of fluorite, celestine, down in Illinois for fluorite down there, witherite, and so forth. So I did a lot of collecting, and that I was based in the East then. It wasn't until I went to school out in West that I had grad school that I actually started collecting out in California. And then somewhere along there, when I was in grad school, I went and visited Tom Warren at Ultraviolet Products, the person I had first bought those first little rocks and the light from. And I spent, I
Okay.
think, $1,000 on minerals there. And he had a whole room full of great stuff. And I prowled in that room and dug stuff out and overturned boxes. I got a great selection of things for about $1,000, and that started me going. Since then, now I've been collecting, and although these days mostly buying minerals, and I do both aesthetics and fluorescence. And in particular, I like aesthetic minerals that are also fluorescent, nicely crystalline minerals. It really it surprises people when they see how nicely their beautiful crystalline specimens also fluoresce. And I've gone to see some of the great collections in the world and shown runners that you can see under UV, and they are all astonished, completely astonished. So that's a little bit
Now,
about
Glenn, there's
where.
a lot of people I talk to. There is a period of early collecting that sparks the interest, and then there is a gap where they
Mhm.
stop collecting for a while and then they come back to it. Did that ever happen to you, or were you always all fluorescent all the time?
Well, no, I was mixed fluorescent and aesthetic. I liked aesthetics, but there was a gap after grad school. I mean, I went to Stanford, and Stanford, I was involved in building up a laboratory and getting some name recognition and getting grants funded and all of that. And so that takes up a lot of your time. I would say it takes up 120% of your time. And you don't have much for anything else. And so that kept me away from it. I was still interested. But then after about 10 years in, I started getting interested again, and things were sort of stable. And I started going to Tucson regularly. I went to my first Munich show. I thought that was fantastic. I went to the first St. Marie show. I loved that St. Marie show. My goodness. Going back, of course, this year.
Oh,
And
super.
that got me going. Then I was buying specimens. I could afford to buy specimens, and I was still collecting. And I've collected in Namibia. I've collected in South Africa. I collected in Australia and uh, Canada, of course. And I hope to actually collect in Indonesia in the future.
Oh, fantastic, fantastic. So it sounds like, especially when you're downstairs and you're kind of overturning a bunch of the rocks, it you really kind of articulate some of the things that really drive the field collectors, which is
Mhm.
it's the thrill of discovery. How
Yeah.
much of that plays into your collecting style these days?
Well, if you're out at a mine collecting, I mean, it depends on the kind of mine. I've been to mines, for example, in Australia, particularly at what's called a deposit called Third Plain.
Hmm.
It's Plain. Um, Everything there fluoresces, every rock, and they're all colorful. So I mean, sitting in a sea of material that you want to collect. So it's all about finding the right one, overturning one, splitting one. It's fascinating. Now, other localities you go to, and there's not too many fluorescent minerals. You have to find where they are, and they might be relatively rare crystals that you have to split up something to find, or you have to find a pocket somewhere and dig for the pocket, particularly with the apatite. So it varies, but there's always the thrill of discovery. And in Australia, the thrill also would be after we've collected all day, and we have maybe 500 pieces, to sit by the fire as it gets dark, and then have a lot of fun with the all those lighting all those rocks up. I'm trying to decide what to take home. So that
Yeah.
gives you some idea.
Oh, totally. Yeah. Arm wrestles over the campfire. No, no, no. I want that one.
Oh yeah, well you have to take turns. You have to take turns. I've done that a couple of times also with buying collections and with someone else, and then taking turns with the. That doesn't work very well actually. If you get the best, if you get the best one on every odd turn, that
I
the other
bet.
person's unhappy. Anyway,
So then it sounds like when you're out collecting and looking at new collections and new minerals, you have to have a UV lamp with you.
oh yeah, yeah.
So, okay, you had said earlier that the UV lamp that you initially purchased was a plug-in deal and it wasn't very powerful. And I know technology has changed so much. Talk to us a little bit about the evolution of UV lamps, both shortwave, medium wave, and long wave.
Sure. Yeah, well, there's a lot to tell you about, but really how things started at Franklin, I'm told, is that they actually used an arc light. So they used a little high voltage arc light to produce a
Okay.
spark, and the spark produced a lot of UV, and they could see willemite particularly, maybe sphalerite too. They could see the ore minerals, which is willemite, pretty well, fluorescing green under that arc light. Then pretty soon thereafter, they realized that they could use a tube, a mercury vapor tube, essentially a Geisler tube, but just a tube like a neon tube, except filled with mercury vapor. You excite that with high voltage, it releases a lot of ultraviolet and several different wavelengths of ultraviolet, but it also releases a lot of visible light. And so they had to find a way to get filters to filter the visible light and just let the UV through. And it turns out you can optimize these mercury vapor tubes. At higher pressure, they emit more long wave. At very low pressure, they emit mostly short wave,
Hmm.
so-called short short wave is also known as UVC, middle
Okay.
wave UVB, and long wave is UVA. And if you have an excimer lamp that works around 180 or something, that would be maybe more an exotic extreme UV, the kind of thing that you use to make semiconductor manufacturing. Anyway, this is the kind of lights they use, these mercury vapor lights, for a long time. Really the same as you'd have in old fluorescent tubes. I mean, that's a mercury vapor light too, but it's got some phosphor inside the tube on the walls that absorbs the
Okay.
UV from the mercury vapor and excites the phosphor to give you white light. And we use those things quite efficiently for years and years, and now they're being replaced with the LEDs, of course. And the LEDs use a phosphor too. They are blue emitting LEDs, and they have a red emitting phosphor, an orange emitting phosphor actually, and the combination of the orange and the blue give you white light. And there's different combinations of that to give you different kinds of white light. But it's really sort of the same principle, but now you have an LED, which is a directed emission in one direction only, not in 360 degrees or four pi. But it's brighter, it's purer, and it's a lot cheaper, a lot less power for the LEDs. So the same thing is translated over to mineral collecting, and now we have LED lights for almost everything. Let me pick one here. This is a typical long wave LED light. This one is extremely powerful. This is 8 watts, and the eight
Hmm.
watts is forward emitting. So I could light things up easily at 50 feet with this. And I have a more powerful light I won't show you that I could probably light things up at 100 yards. It's really powerful. It's because it's forward emitting. It also has a reflector in there to whatever comes out the sides is also forward directed. So it's a very nice light for collecting. In fact, it's too powerful for photography, actually. You'll see a problem probably today a little bit with it. And it took a while to make LEDs that actually operated at beyond the long wave ultraviolet. Long wave is the longest wavelength, and it's the easiest LED to make. It's a little bit harder than making a blue LED, but it can be done. Now, trying to make an LED for middle wave is a lot harder. The electronics are different, the materials are different, and harder to get a decent yield, harder to get things that run at higher power. So it's been a while before we've had middle wave and short wave LEDs, but now we have them. This is a relatively new version of a middle wave LED lamp. This is 295 nanometers. It's a little unusual, but it's optimal for looking at rare earth emission. And then this is a relatively new shortwave light, which I'd like to have more power, but it's pretty good. And all these can be used in the field. I have a holster that has 4 slots in it, and I have 4 different bands, LED bands. Uh, Finally, if this is not enough power and you really want to blast thing, that you could use something like this. This is a UV laser, 405 nanometer. It's a UV visible, right on the edge of UV invisible. And this is a half watt. Actually, I measured it 700 milliamps. It's more like 3/4 of a watt. And this guy really blasts, and it's good to give you another wavelength that's even longer. And it turns out that slightly longer wavelength also does interesting different things with minerals. But it's a laser, and you have to be very careful with this. So usually wear goggles with it. I won't do that today because I have it defocused here, but same. So these are the things you can all take in the field, and I go to shows. These lights are bright enough where you don't need to be in darkness at the shows. You hold the light reasonably close. You don't need any darkness at all. In fact, I think there's a slide that shows a display I put in San Jose. It was for a long wave, and it uses individual LEDs. Yeah, that's it. It uses individual LEDs, which are in little cones. You can see a couple of them there at the top. It has about
Okay.
12 of them. So each one is focused on a different mineral, and this system works fine in daylight. You don't need any darkness at all.
That
And
is
now,
fantastic to have cases like that where you don't need the dark room. That
right.
makes it so much more accessible to the public that's already fascinated by these things.
Oh yeah, absolutely. And this was a very nice exhibition. We printed out a lot of sheets that had a picture of the minerals and also identifying them. So I didn't have to actually have labels identifying them in the case. The labels are a problem. They fluoresce so much with these
Sure.
very powerful long wave LEDs. They fluoresce so brightly, you have trouble making decent ones.
Yeah.
Anyway,
So now, Glenn, you talked about UVA, UVB, and UVC. Which is the one that is most dangerous to us, or are they all equally dangerous?
well, that's actually a very good question. They're not all equally dangerous in general. UVA is also present in sunlight. We
Hmm.
get a lot of UVA. There's UVB and UVC that's produced by the sun, but doesn't get through our atmosphere. So mostly there's UVA. There may be a little bit of UVB gets sun, and UVB is responsible for tanning and sunburn. So UVB is definitely dangerous. It'll tan you, it'll burn you, and it's damaging to the eyes. UVC is even more damaging to the eyes. People that have used UVC shortwave with their minerals, particularly from Franklin, they'll find that they can quickly sunburn or burn their skin. They can quickly burn their corneas and have very like sand in their eyes. It doesn't take long with these powerful lights. These, particularly the old mercury vapor lights, were so powerful they had to ramp up the power to have them bright enough because it was not directed light. They're
Okay.
pretty dangerous. On the other hand, UVA still is dangerous because it penetrates so far. It penetrates well into the eye. So an awful lot of sunlight is not so good for you. You know the phenomena of snow blindness if you're skiing. That's all
Right.
UVA and blue light that's affecting you. So none of them are really good. I try to take precautions when I'm doing not experiments, but when I'm doing work in the field. We wear protective clothing. We're mostly all covered up so that that doesn't happen. Right, especially your face. You don't realize that the UV reflects off the mineral into your face. So
Okay.
if you're doing something for hours, you'd be surprised how much that can affect you. Goggles help. I've had situations where I was collecting at night for hours, and in the morning my face is all red except where the goggles are.
You got raccoon eyes collecting at night.
Oh yeah.
So then, what are some of the kind of early warning signs for overexposure? You had mentioned kind of the feeling of dirt in your eyes. Would
Yeah.
that be one of the primary warning signs or symptoms?
Yeah, absolutely. The first one probably would be really, but by the time you notice that, I think the first I notice it is my eyes feel different. You know, they feel a little different. They feel like the first symptoms of like snow blindness, a little bit of blurring, a little bit of sensitivity. If you get to the point where they're beginning to feel gritty, then you've got quite a lot of burn, and
Okay.
then you want to stop completely. And the next day is going to be a little hard. It's going to take a while. The cornea heals very quickly, but
Oh, okay.
a day or so, or two, you'll be fine. But of course, these exposures don't help you with respect to cataracts. They're going to help to promote cataracts, as far as I know. And all UV promotes that. So that's something you have to worry about.
Okay. It's similar to what they say about drinking. If you feel thirsty, then you're already dehydrated. So, especially
Yeah.
if you're in hot environments, constantly hydrate, even if you don't feel thirsty.
Hmm.
Um, Now, Glenn, prior to me talking to you, I've heard a lot about long wave and short wave. And since I've been talking to you, this medium wave is kind of hitting my brain a little bit. Um, and I imagine there are other viewers who are into UV that might kind of be a new term. Could you unravel that a little bit and explain to us what the medium wave UV is, and when you had mentioned that now with the LEDs that's becoming more prevalent, but has it always been out there? Because I've only heard about the long and the short.
Yeah, it's been out there for a long time. It hasn't been that popular because people didn't realize how useful it is and how many spectacular results you can get from it. As I said, it's particularly effective in exciting a lot of the rare earths, more than you get from excitation with the other waves. But the older lamps were also mercury vapor tubes, and they put a phosphor inside the tube. But instead of the phosphor emitting white light to make a fluorescent light fixture, it emitted mid-wave light. So, and in fact, the same sort of tube was used for long wave. It was a different phosphor. So it was a UV phosphor that gave you long wave. A different UV phosphor gives you a middle wave. And there were different phosphors, and so there are several different wavelengths of middle wave. In fact, 4 or 5 of them, as far as I know. And there's also broad emission with more wavelengths and narrow emission with a tighter range of wavelengths emitted. So there's a lot of different variations in middle wave. We don't see that in long wave and short wave so much because our perception of those wavelengths is tied to the emission of the mercury vapor lamp. The mercury vapor lamp has very strong emission at 254 nanometers. That's what we call short wave, and that's where everybody started studying minerals using the mercury vapor lamp. And then the 365, 366 nanometer emission of mercury vapor is the long wave. So those are the ones that everybody sort of grew up with. Those are two strong emissions of the mercury vapor lamp. And as I said, you can optimize the long wave one by having a higher pressure in the lamp, have a very powerful long wave one for theater works, lighting up a whole stage. Or you could use a lower pressure lamp, quite low pressure, to give you mostly short wave. It's beyond our purpose here, I think, to understand why you get different wavelength optimized as a function of pressure, but it's an interesting thing anyway. But that's where those two wavelengths came from. They came from the mercury vapor emission. And middle wave came in because it was sort of neglected, but people started experimenting with it, and they found, first of all, it has a medical use. People have used it for psoriasis and other dermatological uses.
Huh.
And also people saw that some of the minerals responded differently. And in particular, apatites with a lot of rare earths. I can rattle off a lot of names here, but why bother? A lot of minerals respond very uniquely to middle wave, and so it's a necessary thing to have.
Well, I think that's fascinating. I hadn't heard about the use of middle waves to treat dermatological problems, but talking about that, you bring up an interesting topic in terms of functional use of UV lights in exciting minerals or fluorescing minerals. Um, Prior to our meeting, it always seemed to me that it was more kind of a curiosity, this whole fluorescent minerals. Mm-hmm. But I recently learned through Peter McGaw that during World War II, when we had a tungsten shortage because we had limited access to the tungsten reserves in Asia, that the government started generating a lot of UV lamps and giving them out to the public to do searches within the country for tungsten sources. And it sounds similar to something that you've mentioned a couple times already, which is using UV lamps to identify rare earth elements. Mm-hmm. Do you see that might also be a real functional use of UV lamps to look at other sources of rare earth elements?
It's an interesting question. One of the aspects here that I don't want to dance around is that the level of concentration of the activators, that's the impurities in minerals which actually create the luminescence, can be quite small. And in rare earth minerals, it's can be only tens of parts per million. It could be a very small amount of these things, and that activates it. And if you have more, much more, which is the ore mineral you'd like, it tends to quench the luminescence. You don't see such good luminescence. But still, you could probably trace through the rock units where the concentration goes using luminescence. I think these days probably they have more sophisticated, we have portable neutron activation systems and things like that in Raman spectrometers. The Raman wouldn't be so sensitive, but the neutron activation would, and they could trace them better that way. But UV is useful also for uranium. I mean, the government produced a lot of Geiger counters to look for uranium, and right. But uranium minerals, not all of them, but a large set of them, usually found, some of these found with every uranium deposit, are very fluorescent because it's the uranyl ion, UO2 ion, is extremely luminescent, very bright, very efficient luminescent, and even at very low concentrations gives you luminescence. In fact, it's such a good, and it doesn't quench very much either. So you could have pure uranyl-containing material. It's very bright. The result of that is that if you look around your house or you look in your backyard, you'll always find green fluorescing rocks or objects, and they have some uranium in them. because uranium is ubiquitous. It is everywhere. And
Hmm.
it's one of the first things people find. They go out and they find some green rocks, and people know Franklin think it's willemite. Of course, it's not willemite, it's uranium. And they also made uranium glass called Vaseline glass in the 20s and 30s. A lot of people have them. I have a whole set of them. They don't have very much uranium, but they have enough uranium to color the glass just weakly yellow green, and they are brilliantly fluorescent. It's fascinating. So there is a connection. UV has its application, and it probably has some more applications I don't know about. But I wouldn't say in prospecting. I think we moved to more sensitive equipment, instrumentation.
Okay. Now, Glenn, I've noticed that you're using two terms that I'd like to kind of have maybe each clarified. Maybe you can help us a little bit with that.
Hmm.
You're using the term luminescence and the term fluorescence. What's
Hmm.
the difference between the two terms?
Okay, well, there's a lot of confusion in this terminology, and I think the confusion stems from if you read the literature, you're finding that people use terms all over the place, sometimes at cross purposes. Luminescence is just a general phenomena of emitting light. And there's another form of emitting light which is not luminescence, and that's what they call black body emission. So if you heat something up hot, you'll see it glow red, it'll glow orange, yellow, and eventually even blue. That's a black body emission. It's just thermal emission caused by heating. But the all other sorts of light that's emitted from objects, from materials, even from gases, we call luminescence. So luminescence is the generic term for everything. Now, inside that term, then there's different types of luminescence. You could have fluorescence is one type, which is what we usually talk about when we have so-called allowed electronic transitions in an ion or in a mineral. I'll say something else about allowed versus forbidden transitions later because it's important. If the emission is delayed, if you put a UV light or some other source on a rock, on a mineral, and then you take it away and it continues to glow for a while, then that emission can be caused by several different mechanisms. One mechanism is phosphorescence, which actually is found mainly only in organic materials. And then there's another mechanism called thermoluminescence, which happens at room temperature as well as at higher temperature. And that's what gives rise to most of the delay we see in most minerals, particularly Franklin minerals. It's a thermoluminescent effect. It's not really a phosphorescence in the regular sense. And there's also chemiluminescence, which has nothing to do with UV, which is just chemical excited radicals, which exist due to a chemical reaction. Well, energy is produced in this radical, and that radical decays back and gives out light. So it's actually seen in fireflies as well as in fish, in
Okay.
invertebrates, and firefly. Well, it's called bioluminescence when it's chemiluminescence. It's chemically created, but it's in an animal. It's bioluminescence. There's radioluminescence, where if you excite something with X-rays, it also can luminesce. So there's all these terms about luminescence, but for minerals, the important ones are probably fluorescence, phosphorescence, and thermoluminescence. And fluorescence, as I said, is a loud electronic transition where the UV light is strongly absorbed, efficiently absorbed, and then emitted as the excitation decays back. You essentially get the emission out. There's a little loss of heat in the structure. Vibrations are created, and that's why the wavelength of the light coming out is longer. So that's why UV produces visible light and also produces some infrared light. But you could use green light to produce orange light too. Many minerals fluoresce in the green and produce orange and red. Ruby is a
Wow.
good example of a nicely fluorescing mineral that fluoresces great under green light, but you need to have goggles which block out the green light or you won't see the fluorescence. But anyway, so that's a general principle. I think I have a slide that explains phosphorescence and thermoluminescence, but I don't want to get too complicated for people on these things.
Too complicated for me, please. Let's keep it simple. So my understanding of phosphorescence was always if you had excited a mineral and you removed the source of the excitement, you turned off the lamp. If it continued to glow, it was considered phosphorescence. That my understanding may not be entirely accurate. Because you had mentioned something about a color shift. Now, I don't want to go too deep into it because we want to get to see some of these beautiful
Sure.
things. But maybe real briefly, you can comment on that.
Sure. I'll do it briefly. The phosphorescence term is started with in ancient times, really, or pretty old times, when people saw a glow that continued, and phosphorescence is linked to that discussion of a continued glow. But in more modern times, it's mostly linked to organic materials, which have a particular slow decay rate when they're excited. They can be fluorescent, so you could have this fast excitation, but they also have this very slow reaction, which is a forbidden transition. Turns out that that transition involves another state, electronic state. It's at lower energy than the fluorescence. And so in the phosphorescent case with an organic material, you will see generally a different color of the emission. It's a lower energy, so if fluorescence is blue, you will see green. With some dyes, not minerals, but the dyes that fluoresce in the green, then you'll see yellow for the phosphorescence. And so that's a particular characteristic. We don't actually see this sort of reaction in minerals. But what we get minerals so I said thermoluminescence. And what happens there is that the electron is excited to an excited state in the mineral, in the ion, and then it gets trapped at a slightly lower energy just below that excited state. It's difficult to explain without a diagram, but just a little bit of energy just below. And that energy gap between the two is small enough that room temperature can lift the electron back up to the excited state and it'll come down as fluorescence. So
Interesting.
thermoluminescence is delayed fluorescence when you have an electron that's trapped at an energy a little bit below the excited state. Now, if the trap is deeper, it takes more energy. If the trap is even deeper, it takes even more energy. So the effect is that the electron can be trapped for a very long time, for millions of years. This is the diagram on the right, actually. It's partially blocked on my screen. You can see you have well, I use my arrow here. This is the thermoluminescent case. Here's the ground state, the unexcited state, and here's the electrons up to an excited state. So this is what UV does, let's say. And you could get fluorescence. That's this arrow. But it could also come over here. The electron in the excited state can get trapped over here in this state.
Glenn, I'm sorry. We can't see your pointer as you're moving it. So maybe you can just verbally tell us where to look on the screen.
I'm sorry. So looking at the right-hand diagram, it has a big up arrow and a big down arrow. The up arrow is the absorption of UV light or some exciting light, and the big down arrow is a emission of light. And so the fluorescence in that system would be the big up arrow and then followed by the big down arrow. However, the electron, once it's excited, can also do something else. It can go off to that other state, which you see on the right. It's an electron trapping state. And it's stuck there. It can't emit. It can't fall down to the lower state until it's excited back up to that other state, and then it can come down as fluorescence. So that electron trap delays everything. If the trap is shallow, very little energy below the other state, it can be brought back by room temperature. And so that's what we see in like Franklin willemite. When Franklin willemite has a long delay, we have electrons going into traps. They're caused by arsenic in the willemite structure. And then room temperature pushes them back up to the excited state, and then they come down as fluorescence. There's no difference in color. The emission, whether it's prompt or delayed, is the same exact color because it's the same transition. It's from the same state. So that's what happens. Now, if that trapping level is lower, we call it a deeper trap, then room temperature won't kick the electron out. In fact, the electron could stay there for years, millions of years even. There's nothing to bring it back. The only way to bring it back would be if you find the mineral and you heat it to a high enough temperature to kick the electron back. And when that happens, we all know that phenomenon. Everybody calls it thermoluminescence. But the key thing is that this happens at room temperature too. I hope that wasn't too confusing.
Well, I think the slide really helps out a lot with people trying to understand that. Glenn, let's go to some real world examples. I've got a bunch of photos that you sent me, but I know you also have a second camera there. Yeah. And I'm going to leave it up to you to tell me if you want to go to the photos or if you want to show us some live things.
Well, let's try one line thing first because I'm not sure how well this is going to work because I'm using the wrong side of the camera for some reason. There's a face view and there's a forward view, and for some reason the other camera won't work in this zoom mode. So the I don't know why that's happening. Anyway, it doesn't matter. I've got a mineral set up now. This is an andesite, and you can see it now in white light. Bring the light
Okay,
over.
there we go.
Yeah, you can see that. This is a nice andesite rock. It's about 5.5, 6 inches across. It's from Morocco. And it's characteristic kind of a yellow color. Uh, the first thing I'll do is put it under some long wave UV. Let's see, turn that out. You can still see something.
Hmm.
So this is the effect of long wave UV. You can see
Wow.
it's
Okay, so
got
we have a
a
nice
nice
deep orange red.
orange red emission, and you'll often see this with andesite, but not always. It doesn't have to be fluorescent. Now, if I go to a different wavelength, I'll go to middle wave, the middle wave we've been talking about. And now you see that, first of all, it's other colors. There's orange, there's yellow, and there's little parts of the crystals that are blue-green.
Hmm.
And this is all coming from using, I'm exciting actually zones in the mineral that have slightly different activators. Now I can try shortwave. Shortwave, you just get
Oh,
sort of a
completely
yellow
different.
emission. You're not seeing any of the other things. Well, a little bit maybe. Hard to focus. Anyway, that's an example of two things. First of all, the fact that you can have different emission colors from different activators with different wavelengths, and also the fact we have a very nice crystallized specimen, multiple $1,000 specimen, I guess here, which fluoresces very nice. And you see it if you're actually here in the room with a bright UV on it. It's actually very dramatic. And I'm going to change minerals now.
So you said you had a four lamp holster.
Yeah.
So you take all three lamps with you, and if you find something that is aesthetically pleasing, you put the torch on all three of them, one after the other.
Oh yeah. Yeah. Well,
I
actually,
love it.
I have room in the holster for about 6 lamps, and I have 6 different wavelengths, and so I could. Oh, here's the holster.
Well, I was going to ask if the fourth slot was for a shot of whiskey.
I usually wait until I'm done collecting, but then I prefer wine.
Ah, there we go.
Okay, this particular mineral here I could show you. This is a very nice sample of apatite from Panasquare, Portugal.
Hmm.
It's really nicely crystallized. I'll put it in front of the camera. We actually have photos of this, but might as well do it in real time. You can get
Yeah,
some fun.
live is always more fun.
Yeah, live is almost no time. Put the light out, and you can see here it's going to really blast the camera. But you can see the interesting thing is this is BlueCap Productions, but this is a BlueCap Appetite. Uh, you can see that the faces of the crystal are fluorescing blue, and the body is actually fluorescing sort of a yellow orange. And it's sector zones, so that if you cut one of these open, you'd see like an X inside them.
Wow.
Yeah, and that's we're
Now it
getting.
actually looks like there's a area that is a third color. Is that just the monitor and it's just blowing out, or is there in fact a kind of more aqua color that's showing up there to your eye?
Well, I think it's the camera's blowing out, as you said. It's
Okay.
overwhelming the
All right.
camera because there's so
So it's
much.
just an overexposure of that same blue.
Yeah, this is middle wave.
Oh, we got some of the yellow coming in there.
Yeah, the yellow's coming in. The yellow's largely to dysprosium, incidentally. Now I'm going to try the laser. I don't know how well this is going to work because I don't have a filter on the camera, but
Oh,
that's the
now
laser.
we have predominantly yellow with
Yeah,
some looks like purple, but that might just be like a reflection or something of the light.
yeah, it's the light. If I put a filter in front of it,
Oh,
you can see it's pure yellow, and that's mostly due to the dysprosium.
so what filter is that now?
This is an astronomical filter, which blocks all UV. It blocks everything from um, uh, about 420, about no, about 400 up. So it
Okay, so
blocks the
in
laser.
normal light, that's a little bit purplish, correct?
Yeah, yeah. I put the light back on here. I could show it to you. What it looks like.
Yeah.
Not much. You can hardly see any color in it. It's got a little color, but it's very, very faint.
No, but in the photography world, they have a filter that you put on that I believe is the same one that they recommend you using if you're going to do long exposure shots of the sky to
Yeah,
help cut out the light pollution coming from cities and such.
that's exactly what this is. This one doesn't cut out so much light pollution, but it's optimized for UV.
Ah,
So it's a dichroic filter. It's a special custom-made filter. It's kind of expensive thing, but it's essential for using a filter like this for fluorescent minerals because at least with the phone camera, there's a lot of reflection back into the camera. You can't avoid the reflection, and it fogs everything. It also overwhelms the camera. It's
mhm.
so anyway, that's this guy, which you have a couple pictures of. I'm gonna put it
Yeah.
somewhere.
Glenn, let me ask you, since we're talking about filters, I know that back in 2022, there was that incredible exhibit at the TGMS, 40 plus cases of fluorescent minerals there, kind of celebrating
Mhm.
I believe it was the 50th anniversary of the Fluorescent Mineral Society.
Yes.
And in a lot of those cases, the glass in the front of the case was actually a special glass that filtered something out. Talk to us a little bit about that.
Yeah. Well, glass is fluorescent for one thing, and there's really a couple of things to talk about. Two things mainly. Um, if you just have glass in front of your case, it will cut out a lot of the ultraviolet. It'll cut out UVC, shortwave, and it'll cut out middle wave. It won't cut out UVA though. UVA will get through the glass just like it gets through solar gets through the glass. So are UVA. But most glass it used to be made. I don't think it's made quite the same way anymore. It used to be called float glass, and the glass is floating out on mercury. So one side of the glass has a little mercury in there, and mercury
Okay.
also has some tin in it. And both mercury and tin actually then become activators in the glass, and that side of the glass fluoresces a little bit. So that gives you kind of a haze. It's a very weak fluorescence, but it's a haze. And so you don't want to have that side facing the UV lights. That's say facing the interior of your case. You want to have it facing out. And so it's a good thing. I've seen cases made where they screwed that up, and so it always looked foggy. So they had to take the thing apart, take the glass out, and put it on the other side. But I also use a second layer in my case. I use a type of a plastic which is very strongly absorbing of all UV and does not fluoresce, and that goes over the glass and blocks all UV because the UVA gets through. And when I have a case like that daylight case, it's really blasting with UVA, and it's really
Mhm.
coming out. And people's clothes light up and everything if you don't have. So I have a blocking. I think it's OP3 plastic, which will block that. So it's a little more complicated these days, but there's plenty of information, like in the Fluorescent Mineral Society, about what glass to use, what kind of plastic to use, and the details of this problem.
Super, super. Glenn, do we have more examples that you want to share with us?
Sure. I mean, I have probably too many examples, but I'll.
Yeah, it's kind of like I know that's a dumb question, but it was a prompt.
Well, I have close to 6,000 minerals, so
All right, so this is going to go well over an hour then.
well, it doesn't have to go over. You let me let me know. Okay, this is a Franklin mineral. Um, And as a Franklin mineral, most of them are good under shortwave. This is shortwave.
Oh,
So this is a mixture of willemite fluorescing green, um, hardystonite fluorescing blue, blue purple, and the red fluorescing one is bustamite, which is a nicely fluorescent mineral. Sometimes it's kind of uncommon to fluoresce this well. This is shortwave. I try long wave. The bustamite really lights up kind of a cherry color.
yeah.
Yeah. And these are kind of uncommon specimens. It's hard to find something quite this good. But that's put the light on again so you can see it's a how many people would love a rock like this? I don't know, but it's a nice size. It's beautiful and it's hard to find. Let me get something different. Here's
Well,
another.
I remember I did a film at the Franklin mine, one of the new Crystal Hunter films, and one of the during kind of the end of the show, we went into the Rainbow Room,
Oh
and
yeah.
that was such an incredible experience. And to see it on a film is one thing, but to experience that live, you really start getting why this is so popular.
Oh yeah. Yeah. Well, you see some of the great fluorescent mineral collections, and it's astounding. Your jaw will drop to the floor. Um, this is a specimen of willemite, blue willemite on calcite with a few other minerals too from SUMEP. It's a nice specimen as it is, but under long wave, the willemite fluoresces yellow, not green, but yellow.
Hmm.
And let me go to I forget which light does which with this guy. This is so that's middle wave, and this is short wave.
Wow.
So in the
What a
short wave, the willemite fluoresces kind of a bluish green, and the so I guess you could sort of cheat and try to put two of them on at once.
Oh, there we go. Oh, look at
I don't know
that.
how to do this, but you get the idea. So this is keen stuff. It also shows how interesting willemite is. Willemite fluoresces a blue-green here, but it can also fluoresce yellow. It fluoresces a bright green. This is a different activator than the green, and so on. These specimens, of course, are beautiful just for their aesthetics. It's a nice sized one.
So I'm sorry, what is the activator here? Is that arsenic you were talking about, or is that rare earth elements?
In that particular sample, we have several minerals. The willemite is actually being activated by several different activators. In fact, about six. So it's a little complicated. So it's got a little manganese in it that's giving it a little green, but it's also got lead and other elements, including rare earths, that are causing it to luminesce that color. It's interesting.
Okay.
The calcite's fluorescing mainly from manganese. In fact, let's put on a more common mineral. This is just calcite, except it has two generations of calcite. This is from Peru. In fact, I just picked this up at the last Tucson show. And this
Oh,
is the
wow.
fluorescence under middle wave. You can see several different generations of calcite. One generation is kind of a pink. One of them is fluorescing not very strongly. You can see it's sort of like in balls. And then there's one that's brighter orange yellow. This is a mixture of manganese emission and rare earths. The rare earths are adding the blue into the what ordinarily would be red. If I try this with long wave, then you just see mostly manganese emission, and you see mostly just orange. Unfortunately, got a lot of backscatter from the source. And if I do shortwave, and you see another different combination. Again, blue
Interesting.
emission there in part from rare earths, and mostly manganese is giving you the red. And this is just sort of common stuff from Peru, not a particularly expensive sample, but beautiful stuff. It's actually a pocket in galena that has this. Put the light back on. Not a bad aesthetic specimen too.
Now, Glenn, how many people collect the same way you do, which is by color and aesthetics?
Uh, yeah, okay. I don't know.
Okay.
I got to move my light here. Yeah, that's better. Um, I don't know, actually. I mean, a lot of people collect just if it's pretty. The
Right.
prettier it is, the more impressively bright it is. I think a lot of Franklin collectors are kind of like that. But other collectors, they get into the scientific side. And I have a lot of pieces which are not particularly pretty to look at, but to me, they're interesting. They have exotic activators, they have funny colors, they're rare for one reason or another. Um, but it's different things for different people. If you go to the Fluorescent Minerals site at Facebook, I think it has about 13,000 members now, something like that. So there's a lot of
Wow.
people that join that site and look at what's happening. And there's an interesting discussion about lights, about minerals. People post spectra. So there's people doing spectroscopy, not just me, but many people. And they're very knowledgeable people there. It's quite interesting. Let me show another one here that I think is it's too big, but I'm going to put it here anyway, because it's a very popular mineral. It's too big to even put in the frame, even if I back up, but it doesn't matter. Um, Oops, wrong filter. This one. This is tugtupite from Greenland.
From Greenland.
From Greenland. Very popular place to collect, actually. It's a very high alkaline pegmatite, and you get this very pretty, this is chaclavite. The green mineral here is chaclavite, and the tugtupite is the red. And tugtupite fluoresces orange in, whoops, really blasting. Orange yellow in long wave. I have to hold the light way out here so I'm not overwhelming the camera. In fact, it
Wow.
looks more yellow. In person, it looks more orange.
Okay.
What does it do in mid wave?
Oh,
That's middle wave. But now the chaclavite's really lighting up. Chaclavite's got rare earths and uranium in it. Pretty, huh?
very
This
cool.
this is very prized. Tugtupites are very prized and very valuable. So that even though it's not really a crystallized mineral, these guys really command high prices. And this is a big one. This is about an 8 pound piece. Let's see if we have something else which is particularly unusual. Uh,
Glenn, I'm sorry to do this. Let's do maybe one more, and then I want to
okay,
show that video that you sent me
okay,
because we are already about an hour into the show, and then we'll give
okay.
the viewing folks a chance to ask some questions here.
Well, let's do one more that highlights phosphorescence. This is a gypsum crystal from Germany. A lot of gypsum does this. Turn out the light. You can see the fluorescence for it. It's quite bright, kind of a bluish white. And you can see the phosphorescence. And
Oh,
this is true
sure.
phosphorescence. It's a different color, so-called triplet phosphorescence. A lot
So
of
it's got the
gypsum does.
afterglow and a slight shift of the color.
Yeah, really blasted here. Yep.
And which UV lamp is that again?
I'm using long wave, but I think almost
Long
anything
wave.
will work. I don't know if I try, this is middle wave. Looks a little bluish, actually, the more bluish this way. I may actually be activating something different.
It seems like that one is slower to release the glow.
Yeah, there's another, I'm activating something else with this wavelength. It may be another mineral present. Yeah, fascinating.
Yeah.
Yeah, there's still something glowing there after all that time. It looks like it's very slow.
Yeah, we can't see it on the camera.
Yeah, it's very
And
low.
then what does it look like under short?
Oh, under short. Okay, let's go back.
That seems even slightly slower to me.
Yeah, it does. And it's not as shifted as much. It shifted less. Could be we're actually exciting different. There's a lot of organic molecules in these materials, not just one organic, but they often the organics come from leaves and organic material that's present while the gypsum's growing from whatever liquid it's growing from. So there's a range of chemical compounds, and each one could have a slightly different absorption and a slightly different emission. So
Now, would something like that be a catalyst for you to get it deeply analyzed, looking for what the composition is?
yeah, you could. Trouble is with something like this, when it has a lot of different things in it, you probably have to dissolve it and use something called gas chromatography or gas liquid chromatography to analyze it. These days we can do chromatography by ablating it and analyzing the gas coming off from burning it away, essentially.
Jeez.
It's complicated and expensive, but that's one of the ways you analyze something like this if you really need to know it. And there are people that are very interested in luminescence from organic materials because they give you an idea of what's happening in the soils over time and also in the formation of sedimentary rocks. It's actually a rich area, and it does use luminescence. My friend Satish Mainini, a former postdoc of mine, he's a professor at Princeton. I work with him. He analyzes these things in detail. He's very interested in the differences in the organic molecules and how they change with time. They break down in the environment as well. He wants to understand how the chlorine is released from them when they break down. They're often chlorinated hydrocarbons. It's interesting to know that chlorinated hydrocarbons are natural. They're not just produced by industrial production. Leaves have chlorinated hydrocarbons and so forth. It's an important part of the chemical machinery of the leaf cells. Anyway, so that's complicated. It's a simpler analysis in the terms of the other minerals. It's an inorganic analysis, so we're looking at the different types of trace metals and so forth. It's easier to do. You can do a relatively decent analysis with fairly simple instrumentation. George Rossman has a very nice small X-ray fluorescence system, which does a good job. And then you could do high resolution X-ray fluorescence or use an electron microprobe, which also uses X-ray fluorescence. And these things can analyze things quantitatively down to very small percentages. So different ways, different approaches.
Fantastic. Well, I'm going to ask Eloise to go ahead and launch the poll. And so, Glenn, you're not supposed to see that. So close that window. In the meantime, what I'm going to do is I'm going to queue up this video. Now, this video doesn't have any audio. So, Glenn, I'm going to ask you to narrate what is going on in this video because I find this absolutely fascinating.
Okay.
So there we go.
Okay, unfortunately, I'm blocked out. I have to close this thing here. Okay, yeah. Yeah, it's this is willemite, fibrous willemite from Franklin, New Jersey, which fluoresces very nicely, and you see it has a long afterglow. Steady afterglow is the genetic term we use for delayed luminescence. So I'm going to cool this in a dry ice acetone bath. You can see that there's a dry. I don't recommend being very careful if you try this at home because the acetone bath will wet your fingers, and because it wets your fingers, it'll transfer the very cold liquid. So it's dangerous, more dangerous than liquid nitrogen, probably. Okay, now
remember, kids, Glenn had exploding chemistry sets when he was a kid, so he's a professional.
So now you can see something. Where I've cooled it down, you can see that it doesn't emit as much light.
Right.
What's happening? It's because there's not enough energy to release the electrons from the traps. So they're stuck. A lot of them are stuck anyway. There's some fluorescence, but there isn't much of the delayed luminescence. Now I'm going to put it in hot water. When I put it in hot water, you'll see immediately that the luminescence increases, the fluorescence increases. There it is again. And you're pumping out the traps. You're kicking the electrons out of those traps. They're in traps produced by arsenic in the structure. And that's an example of thermoluminescence, except here it's at a little bit above room temperature. It's at hot water temperature. But it's the same thing happens at room temperature. You can see that these guys continue to glow for quite a while. And I'll use that term again, afterglow. It's a totally generic term for any glow after you take the light away, and we can call afterglow. And we don't have to call it fluorescence, we don't phosphorescence, thermoluminescence, whatever. Just say afterglow.
Superb. I love that. When you showed me that video, when you sent that video to me, I was totally excited, and I promised you that we'd use it in the show.
Okay.
Glenn, we've got to end it there because we are slightly over an hour. But before we go to the Q&A, I'm going to do the quick fire 5 with you. Now, these are 5 questions. Each question has 2 answers. You tell me which answer you resonate with most strongly. All of your answers are correct. The viewers have already voted. They've tried to predict how you're going to answer. We're going to see how well the viewers have guessed your answers.
I already gave some of this away, I think.
Oh, yeah. That's the point. I mean, if the viewers have been watching, then I think most of these should be fairly simple. So, are you ready?
Mm-hmm. Yes.
Okay. Question number 1, wine or beer?
That's a tough one. Wine.
Wine. Okay. Question number 2, most important tool for a night hike, Flashlight or UV lamp?
Actually, it has to be a flashlight, otherwise you fall down. You have to have both.
See, the practicality and the safety comes out. I love it. Okay, number 3. This is a very tough one, so listen to both answers very carefully. Best mineral show for fluorescent display, TGMS or the TGMS?
Well, I'm not sure about that. Let's see. I guess it's TGMS.
That is actually the correct answer. And that's referring back to the 2022 TGMS show where I'd mentioned this earlier. We had a fantastic fluorescent exhibit, 40 plus cases. I think it was something like twice the number of cases that were used 25 years earlier when they did a similar thing. And if you hung out by the exit and you heard people coming out, they were just astonished, jaw on the ground. So, you know, largely in part to people like Al Liebetraut, Walt Donovan, Don Newson, and the entire Fluorescent Mineral Society.
Absolutely.
So absolutely wonderful exhibit. Thank you to the TGMS and everybody participating in that. Okay, question number 4. Preferred UV wavelength, long wave or short wave?
That's actually tough because the long wave lights are so much better now and they're so powerful. They light up almost everything. I'd actually say long wave.
Long wave.
Now. Right now, it's subject to change.
Subject to change, of course. At this moment in time, long wave. And final question, favorite fluorescent mineral, calcite or willemite?
Well, probably willemite, although calcite is pretty interesting. There's a lot of varieties of fluorescent calcite, all sorts of colors and reactions. So, but willemite is special, and there's still a number of problems in trying to understand willemite luminescence.
So it's the unanswered questions that really kind of grip you.
Yeah.
All right. Eloise, I assume you're the one who is going to let us know how our viewers did. Is that correct?
I think that's correct, Brian.
That's correct. Okay. Question number 1, wine or beer? It was a tough choice, but Glenn ended up leaning more towards the wine side. What did our viewers say?
People have been listening to this interview. 94% said wine. That's everyone.
Well, there was the fourth slot. There was the comment that the fourth slot in the holster was for whiskey, and he did clarify, no, I would probably go more for wine. So there was that giveaway there. Context clues, people, pay attention. Question number 2, most important tool for a night hike, flashlight or UV lamp? Glenn surprised me by actually going with flashlight, and I can't disagree with that. But what did the viewers say?
He surprised everyone. So everyone, like 87% said UV lamp. Come on, we can't blame anybody here. Okay.
Well, I've done hikes with just a UV light, and you fall down a lot.
Well, it doesn't mean you don't have body armor and padding. I mean, it's just come on. This was probably the next question was probably the toughest one. Favorite mineral show or best mineral show for fluorescent display, TGMS or TGMS? Glenn went for TGMS. What did the viewers say?
TGMS, but we should have said TGMS 2022.
Oh, okay. Next time.
I might add, I make a point is that I go to the other large shows in the world like Munich and St. Marie, and you don't see much in the way of fluorescent minerals there at all.
No, at least there's always a corner at TGMS where they have this fluorescent exhibit. So yeah, you're right.
Well, Glenn, I'm looking forward to seeing you at St. Marie this year. So
yeah,
maybe we can have a glass of wine together.
Sure.
And Elo, if you change your plans, you got to come and you can join Glenn and I with some wines, maybe some bubbly even.
Yeah.
Okay. I
usually walk around with wine at St. Marie.
How come that we never met before? I don't understand. Anyway. Okay.
All right. Question number 4, preferred UV wavelength, long wave or short wave? After a little bit of consideration, Glenn went with long wave. What did our viewers say?
Yeah, it was 64% who said long wave as well. And I think that's, the new lights make a big difference indeed with the power that they have, the intensity. So
Yeah.
yeah, that does the trick.
Certainly. And final question, favorite fluorescent mineral, calcite or willemite? Glenn went with willemite. What did our viewers say?
Yeah, Willemite, 85%. Good job there, I think.
That's 4 out of 5. I dare to say that is a glowing response. Sorry, low-hanging fruit there.
Very.
All right, Eloise, any questions from the audience that Glenn can answer?
Okay, before the question, sorry, I have to say something. Glenn, I've been writing your name. I know how to spell your name very well because I've been writing your name for over 20 years now.
Really?
You're such a big deal in the spectroscopy community and the luminescent community, I mean, you are the god of spectroscopy and luminescence. So I'm super happy to finally meet you in person, kind of. I hope that we can meet in real life. But like the work you have been doing, it's such a big deal in the scientific community. So thanks for joining us today. It's really an honor to finally meet you.
Well, it's
And
very
now we
kind.
can.
Whoa, Glenn, dude, she called you a god. I heard it.
Well, yeah, I have to give George Rossman a lot of credit for enabling me down at Caltech. And let's face it, the person who has, put mineral spectroscopy on the map is George Rossman.
Yeah,
I know,
certainly.
but George is my first god, so it's fine,
Okay.
It's okay.
Oh, okay.
Hey,
Okay.
Glenn, before we get to the questions, I want to give you a chance to briefly talk about, I believe you're working on an upcoming article in Elements magazine with Peter McGaw. Do you want to give us a kind of a hint on that?
Yeah, there's going to be a whole issue of Elements magazine that's going to be about luminescence. And so it's going to have luminescent gemstones, luminescent minerals, luminescence used for analysis of minerals. So it'll have cathodoluminescence, which is electron excited luminescence. So it's going to cover the whole field of what's important, I think, in mineral chemistry and geochemistry. I have one chapter in it which which is involved with the activators, how activators work in minerals, and I think it's going to be a great magazine. It's going to have a lot of great pictures too. So buy it.
I think we can say that I will have an article on it as well with some other
Yeah.
co-authors from France as well. So buy it.
Super. So if we're talking to the gods of luminescence, that might be the Bible. So
No, we
Fine.
only deal with in my case mostly diamonds. So we use a lot of luminescence for the property of diamonds. So
Yeah.
okay. And actually, that's probably one of the questions. I'm going to lead to that question first that I saw somewhere in the chat. Is UV going to become more useful to distinguish synthetic from natural diamonds?
Hmm. I don't know. That's a good question for Emmanuel Fritsch, I think, better than I. But it could be. It could be. Diamonds are mainly luminescent from UVA, and now we have other sources of UVA. We have excimer lasers, which produce or excimer. Well, I have a portable excimer right here. I didn't show it today. Um, these other wavelengths may be very useful in determining that. I don't know though. You can make synthetic diamonds very, very good, and mostly what they have that's different from naturals is that they don't have quite the same inclusions. Natural diamonds have inclusions of boron and nitrogen and so forth. And the synthetics have some of these too, but they also have metals that come in from the liquid metal that they grow in. So there's a little bit of impurity there. So I don't know if UV will help. It might. It might. I think maybe ramen would be better. Micro ramen, perhaps. But you'd have to have micro
Actually,
ramen that could go into the mineral deeper.
Actually, one of the main tools for labs, gem labs, is the diamond view, which uses luminescence. So before even going through spectroscopy, people will put the diamond into this diamond view and see and look at the luminescence, and the growth sectors will be different from
Yes.
natural synthetics. So octahedral versus cubic for synthetic diamonds. Cubic is a synthetic diamond. So it's easy actually to see the difference sometimes through luminescence, thanks to the diamond view machine, if you want.
That makes sense. Yeah, the
Yeah.
growth, of course, of the synthetics are so fast, so it
Yeah.
probably does have a different route.
And for us, photoluminescence is the big deal as well. And we actually cool diamonds down to low temperature to actually fix that emission, so it's easier to look at.
Mm-hmm. Mm-hmm.
Okay, going back to the first question, who built and where did you purchase your display cabinets that you showed at the very beginning of the interview? Because this person is anonymous, so I cannot tell you his name. Is having a hard time finding a good display case to show his fluorescent minerals.
Well, the cabinet's based on cabinets that were made earlier just for aesthetic minerals, but I built it. So it's a copy essentially. And it has been copied by other people too. So I have another friend here who's big into fluorescence as well as dinosaur bone fluorescence. And he's
Yes.
copied it. And I think he has a brighter display than I do. Really, I think you can get designs also from the Fluorescent Mineral Society. There are people that belong to the Fluorescent Mineral Society that build cases particularly for fluorescence, and they probably have blueprints and plans of that sort. Um, so that's what I would do is contact those people. Um, they have a website.
Okay. All right. Maybe we can put you in touch with that person if he's still in the chat over there. All right, next question. We're talking about UV burning your eyes and burning sometimes your skin, as you were saying. And the question is, does suntan lotion helps the skin with the UV lamps?
I don't know about suntan lotion, but sunblocks do. So if you want to wear trouble is with a sunblock, you don't put it over your eyes. So the only thing you could do is, I mean, it's on the skin, and it will help. There's no doubt about it. It will help. Most of it's made for UVA, UVB, but some of it now it will say it's also UVC. And I think the Fluorescent Mineral Society and other people have tested it to see which are the best ones. But basically, it blocks all of the ultraviolet. But you should wear goggles or glasses to protect yourself, your eyes, actually.
Yeah, for
Yeah.
sure. All right, next question. So I guess we're coming back to the display case. Did the individual long wave LEDs in the case have filters for the visible light?
Yes, they did. Mm-hmm. You can
Okay.
you can build a case without filters, lights without filters, but they do emit a fair amount of visible light, and so you don't get as much of a clean fluorescence, and particularly for photography than you'd like with the filter. So they mostly all have filters. That case had filters made of glass, popularly used and popularly available filters. But the new filters are dichroic filters, so they're multi-layers and they're interference filters, and they work much better in general. They don't deteriorate. They're narrow bands, so they can block the specific UV that you're using and allow the other wavelengths to go through. So that's going to change the game a little bit. Most of the lamps I'm using now all have dichroic filters. They're more expensive, but as I said, they work better and they last indefinitely as far as we know. So yeah, all the lights had filters.
Okay, good. Thank you. Howard has a very specific question. Is asking you, do you ever use the term Jablonski diagram? He just heard that term recently after collecting minerals for 60 years.
Jablonski diagram is as a diagram. I don't know how old it is, but it's fairly old type of diagram used for looking at luminescent electronic transitions. It's essentially the diagram with the flat states. It's just a horizontal line. So it gives you the basic idea of what's going on without actually showing the details. I actually don't use a Jablonski diagram except in a slide like we showed. Usually we use a more elaborate diagram called what's it called, a coordinate diagram, which shows how the states vary in energy as they vibrate. It's a little bit configurational coordinate diagram. It's a little bit different and more complicated diagram, but it actually is more closely related to what you actually see, and you could actually do calculations with it. But the Jablonski diagram is one of the older diagrams, which basically shows phosphorescence in organics and luminescence, and as it has the states which are flat. In other words, there's no horizontal axis. There's a one axis which is energy, but there's no horizontal axis. In the configurational coordinate diagram, the horizontal axis is important, and it has to do with the interatomic spacing.
Okay, so we cannot switch. We cannot remove a lot of
No.
things,
All right.
information. Otherwise, you lose. Yeah.
You lose them. Yeah.
Yeah. Okay. Patrick is asking, can you recommend a currently available book suitable for beginners or at mid-level regarding luminescence?
Yeah, that's a tough one because normally what I see are books which are very simple and don't really explain much, but they're enjoyable reads and they give you some information and it's nice. And then you take a step up from that, they tend to get so technical that they're hard reading for a lot of people. I like there's a book by Blaise, Blasse, which is a book. I think it's called Luminescent Materials. Hold on one second, see if I have it here. I don't see it, but I believe it's called Luminescent Materials. I think it's Blaise and Grabmeyer, and it's a fairly good reading on how luminescence works without being too terribly technical. A lot of people are going to find it quite technical, I'm afraid, but it's actually very easy reading. It's sort of a college level, beginning college level. It's not high school level, but it explains really everything so that you can understand all the phenomena if you want.
Okay, found it on the internet, so I copied the link to the
Yeah.
chats for people interested.
That's my go-to. And there are better books that explain things in more detail, but unfortunately they're too complicated.
All right, so Barbara knows her fluorescence. She's asking, is it true that iron and sometimes vanadium quench fluorescence?
Yes, absolutely. Well, iron is a very interesting element. It does quench fluorescence, but it also activates fluorescence. And in fact, that's how it quenches fluorescence. It absorbs UV so strongly that nothing else will fluoresce, but then it can emit itself. So you'll often see beautiful red emission in various elements. In fact, tugtapite that I showed, the red emission is largely from iron.
Okay.
It's very interesting. Vanadium also can quench. There's several different ways to quench fluorescence, but the main way these elements do it is they strongly absorb the UV, so it doesn't get to the other activators. And so that's the main reason. But quenchers can be activators. They themselves can be activators. So
okay, so tugtapite is caused by iron.
Yeah, I mean the principal activator is the disulfide ion. The disulfide ion gives you that bright orange under a long wave, but when you put shortwave on, you activate the iron in addition.
Okay, I see. All right, cool. Another question by Michael, is the yellow fluorescence of fluorapatite activated by dysprosium or manganese, or both can activate the fluorescence?
Both activated. The emission of the manganese is a broad band, so it covers a lot of wavelengths. The dysprosium is sharp, and the very bright long wave yellow emitting things you see from Afghanistan apatites, they have a lot of dysprosium, but they have other rare earths too. So that's why when you have apatites, you often see them orange or yellow, sometimes purple and pink, sometimes blue. A lot of this is all rare earths, but it does have manganese in addition.
Actually, a related question, how do you know what activator it is?
Well, that's what I'm doing at Caltech. I mean, you can analyze the emission, and once you have a very good spectrometer, you get a very high resolution spectrum of the emission. You can analyze what the peaks are from, and you also know if it's a broad band, it's probably going to be manganese 2+. Rare earths are sharp bands, so you can usually identify them. Most things that have rare earths have a lot of rare earths. It's a lot of things to identify. But that's only one way. The other way to do it is another kind of spectroscopy where you hold the you have a couple peaks in your spectrum. Let's say you have a manganese emission, nice red. You put the spectrometer on that red, and then you scan the excitation wavelength. You scan right through all the UV wavelengths. With certain spectrometers can do this. When you do that, you'll see what UV activates the manganese. Not all UV activates. Some of it will be weak, some will be strong. You'll get a structure. You'll get peaks in the, and that structure, electronic structure, is exactly the spacing of the electronic states in the manganese. So that way it gives you a fingerprint, an electronic fingerprint of what the material is. So it's actually very valuable. I know it's a little hard to explain it, but it's a related type of luminescence spectroscopy where you have two spectrometers, one excites and one analyzes. You do them both. Pharmaceutical companies scan them both and make a matrix of excitation versus emission, and that identifies certain aspects of drugs for analysis.
Interesting. I didn't know that use. Cool.
Mm-hmm.
All right, Adolfo. Hi, Adolfo. Nice. Long time since I've seen you, but he has a question. Anyway, are there any differences with the UV observation of triboluminescence?
Oh, that's an interesting question. Something I really toyed along with when I was sort of a kid. I wanted to know about triboluminescence. Well, triboluminescence is complicated. There's triboluminescence you'll get if you break Nico wafers or sugar, sometimes sugar crystals. You'll see a flash of light, and you can also see it when you grind or break up quartz. You'll see emission. Some triboluminescence is actually electrically produced fluorescence. When you crack the rock or break the rock, it produces a high electric potential right where the crack is, and that crack actually ionizes the air, and we see argon emission or emission from the air in the vicinity. Other triboluminescence is different. The electrical produced in the material actually stimulates activators. So you get an activated emission. So, for example, you could break up some calcite and see the red emission from manganese. That can happen. So there's a couple different mechanisms that produce triboluminescence. You can also take electrical tape, and strip it off. And right where you're stripping the tape off, you can see triboluminescence. In that case, you're breaking bonds with organic molecules, and that's luminescing. So it's interesting phenomenon. UV, I don't know. I don't think UV has any particular direct relationship. Maybe I'm missing something.
Okay. All right. Thanks. That was all that was in the Q&A. In the chat, I think you pretty much answered the questions right away. Okay, I think that's pretty much. Rachel was asking about, commenting about cathodoluminescence as well. She says that optical cathodoluminescence is the coolest. I agree.
Oh, yeah.
It's kind of cool, especially on diamonds again. That's really cool.
Yeah, I didn't mention something. I mean, we're talking about the electron traps and everything. It turns out that you can also excite the electron from a trap and produce the fluorescence if you use an optical method. So in fact, it's fun to take willemite that's been excited and it has long thermoluminescence and use like a red laser. You could write on the willemite with the red laser and see your name because it's pushing the electrons up and then they're decaying down and producing fluorescence. So it's the same thing. I don't know what you'd call that. That's optically stimulated luminescence, OSL. It's actually a popular technique to analyze luminescence in surface rocks to tell how long they've been exposed to light. Anyway,
that's pretty cool.
It's cool, yeah.
I know that George was kind of answering and commenting as well on a few things. Oh no, that's another George here. He said wolfenite often fluoresces more when cooled. Kitchen freezer? I don't know, like exactly.
Yeah. If you put wolfenite, not all wolfenites, but if you put most wolfenites in the freezer, or you put them in dry ice acetone, they will fluoresce a lot better. There's two effects. One effect is that when you cool things down, generally they're more efficient. They absorb better because thermally heating any fluorescent mineral damps out the fluorescence. If you heat it hot enough, there's no fluorescence because you're mixing the excited state, you're vibrating it like crazy, and that bleeds off all the energy, so you don't get any fluorescence. On the other hand, there's another effect. When you cool something down, it also moves the absorption bands around a little. So in fact, it can absorb UV a little more, and then it excites. So you got two effects.
Cool. Luminescence is cool.
It
Okay,
is cool.
that's we should.
You can get hooked. You can get seriously.
I could see collectors everywhere now putting their wolfenites in the freezer.
Beware, it can crack.
Exactly.
All right. Thank you very much, Glenn. I think that's pretty much all the questions I've seen here.
Okay. Well, thank you.
Super. Well, Glenn, thank you so much for coming on the show. Fantastic show. It was excellent to get to know you better. I can't wait to have a drink with you in Sainte Marie. For all the viewers out there, thank you for tuning in to another exciting episode of Mineral Talks Live. Come on back in 1 month, June 5th. We're going to have another fantastic episode with another great guest. Until then, aloha, be well. Take care.
Bye-bye.